I'm Rahul Malik. I work for the Canadian federal government in the Office of Energy R&D as a senior science and technology advisor. Prior to joining the Canadian government, I did a PhD in material science where I worked on LFP cathode intercalation. And then after that, I was one of the founding editors of the sustainable energy journal Joule. And then I did a brief stint or a couple year stint in industry, working at A123 Systems as a cell modeling and validation scientist, and later at Camex Power as a battery scientist looking at nickel-rich cathode materials. Today, I will be presenting two interrelated work products from our battery innovation team in the Office of Energy Research and Development, namely the strategic approach to battery innovation. And then I will speak about, we'll take a snapshot of the Canadian battery ecosystem. Before going to the next slide, I want to acknowledge some significant contributions from my team. Fellow team members Renee Silva and Cohen Burtons at my working level, and then my manager Catherine Thompson, who managed and guided this work. My director Jennifer Hiscock, who approves and endorses this work, which means a lot. And then I would be remiss if I did not acknowledge the significant contributions from student interns. First, Andrei Jukic, and then more recently, Montasir Huck, who did significant data analysis and visualization of the Canadian battery ecosystem. Before we get into the battery work, I want to introduce the Office of Energy Research and Development for context. In one sentence, OERD, as we abbreviate it, leads the Government of Canada's efforts in delivering energy research, development, and demonstration funding. In two sentences, we also provide consultation and non-funding supports to a broad energy-interested audience, in my case, science and technology advice, with a goal of influencing the pace and direction of energy system transformation. There was a battery innovation team, but there are also a total of 14 portfolios across energy and decarbonization technologies, and we align our efforts along three key missions. To describe it in a condensed way, it's energy efficiency, accelerating electrification, developing cleaner fuels pathways, and then a cross-cutting mission of reducing reliance on diesel in rural, remote, and indigenous communities. So batteries play major roles in those first two missions, in energy efficiency and electrification, and also in the cross-cutting mission. A little bit more detail about our funding supports. Funding recipients, or OERD funding recipients, they are broad across Canada and are inclusive of government labs and agencies, as well as the private sector, academia, utilities, and others. And to get an idea of the scale of funding, the program that funds the government labs and agencies, called the Program of Energy Research and Development, has averaged about $46 to $47 million a year recently. And then the Energy Innovation Program, which is our flagship program, which namely funds private sector, academia, utilities, and others, has been averaging about $70 million a year, both in Canadian figures. So now a little bit more about the battery work. So OERD's strategic approach to battery innovation, or the SABI as we call it, was released in March 2024 as a comprehensive articulation of OERD's work in the battery innovation space for a broad variety of stakeholders across academia, industry, government, and coming from different disciplines, be it technical, policy, economic, and then different levels of experience with batteries. I'm going to go a little bit fast through this slide because we'll revisit some of these concepts in the next slides. But overall, the SABI was intended to be a coordinating and communicative tool that informs both our funding and non-funding supports. And we organized it around three overarching pillars. First being what is the so-called energy trilemma, which is balancing the environmental, economic, and security value proposition of batteries. And then the second and third pillars focus more on stakeholders or people, namely firms. I won't go into too much on detail now on firms, as the back half of the presentation will focus on that. But well, I'll I'll make one sentence elaboration on innovation infrastructure, which is an interesting concept that references institutions and structures that catalyze and multiply innovation. For example, providing physical assets for R&D, developing skills and workforce, and facilitating local and global collaboration. So the innovation infrastructure and firms, they're placed side by side as a way to show their interaction and synergy. So now I will focus on these frameworks for understanding battery innovation, which is really the crux of the SABI. The pillars shown on the previous slide could, in truth, apply to any energy technology, not just batteries. So the battery-specific context is really highlighted here. And there are 5 conceptual and technical frameworks, and these were selected by us as a way to offer a structured, quick, and accessible entry points, but with room for significant depth for thinking holistically about any particular battery issue, innovation included, and recognizing that advancement of batteries in society requires extensive collaboration and collective action across a vast range of disciplines, expertise, and experience in batteries. So I mentioned academia, industry, government, but we can extend this to practitioners, investors, the general public, people working in the upstream and the downstream of the value chain, and different battery applications, be it defense, stationary storage, mobility applications. So I figured this audience knows or skews more towards battery practitioners. So I strongly recommend using these frameworks as a communicative tool to explain the value proposition of your battery interests and endeavors to a broader audience as a situation arises. And if the frameworks seem obvious to you, that means they are working, and that is the intended effect. For us in OERD, we have sought to operationalize these frameworks, which is a concept that came from my manager, Catherine. And that is to align our thinking within our organization, to shape our funding calls, to guide our data collection, measure our progress, and structure our communication. So I will spend the next 5 slides going into some detail on these 5 frameworks. And you can find even more detail in this peer review paper, which I encourage you to cite. So the first battery framework is the battery sustainability framework, which is a high level, more of a social and goal-oriented big picture framework. And that echoes what was shown as the first pillar of the SABI, which is considering the energy trilemma in a more directed way for batteries. And we have that represented in this figure where the inner ring shows those 3 drivers, innovation drivers, and environmental, so decarbonized transport and power, economic, industrial transformation and competitiveness, and then supply chain resiliency. So the first pillar of the SABI is represented in this whole picture. We can see pillars 2 and 3 in the industrial transformation and competitiveness in this middle ring, which are essentially pathways that describe ways to get to addressing innovation needs and opportunities, which are reflected in the outer ring. So we have supporting innovation infrastructure and growing innovative firms. And then there's also an equity piece, which refers to building a skilled workforce, making batteries affordable, and in our case, being the Canadian government, addressing underserved Canadian use cases, be it low temperature or addressing the needs of sparsely populated areas separated by large distances. I'll speak a little bit about the environmental piece. So there's 2 main aspects that we can see that batteries offer value. So one is in supporting net zero applications, be it displacing emissions from mobility, on-road or off-road, or being the stabilizer and enabling storage of renewable energy as stationary storage. But we also need to consider the environmental footprint and costs of building that value chain, and thinking about clean electricity input, battery circularity, and decarbonizing the value chain. Last and certainly not least, and it's really come to the forefront in recent years, are the resilience and supply chain value proposition of batteries. So a big part of thinking about batteries is the upstream and the reliance on critical battery materials and chemistries, but also the opportunity for substitution and employing abundant battery materials and chemistries. And in terms of stakeholders and interactions between parties, thinking about cooperation, trade partnerships, and then to build resilience, decoupling from unreliable supply chains. So if this gives you the why, now we're going to the next framework, which is more of the how and the what. And this is the anatomy of a battery framework. Technical frameworks are also essential to assess the value of any battery proposition. And even though most in this audience will be readily familiar with this picture, I think revisiting it reveals some of the core strengths and the challenges of batteries. So first, at its most general level, a battery has three main components: the anode, cathode, and electrolyte. And this is true not only for lithium-ion batteries, but also for alternative designs, be it metal, air, or flow batteries, which have analog components. And the electrochemical energy is stored in the anode and cathode. They're separated by an ionic conductor, which facilitates electron conduction through the external circuit. So this is the high-level description and operating mechanism of a battery. And just from this level of analysis, we can see the core value of a battery is its high energy conversion efficiency from chemical to electrical energy and vice versa, which in some instances can be over 90%, and its ability to be reversible, to reversibly charge and discharge for, in some cases, thousands of cycles. So if we can compare that to fuel-based conversion, which is a one-time process with lower efficiency, the value of a battery is apparent in terms of less materials intensity and less waste. On the other hand, fuels are more energy dense, and in the suite of clean energy technologies, batteries are actually very materials intense due to the strict relationships between the quantity of electrical energy and the amount of material needed, just driven by the electroneutrality requirements. So beyond those core points, which are important pieces to communicate about the value of batteries, understanding the value of a battery proposition, one must have a working understanding of its components and operating principles. And with some baseline familiarity at this level, one can go deeper and explore more detailed concepts, such as the things that we heard about earlier in the session, whether it's coded separators or form factors, or things like a solid electrolyte interface. They all require an entry point of this level of understanding. I just mentioned and motivated the materials intensity inherent to batteries. And so that motivates consideration of the entire battery value chain, from exploration and mining to end use application, and end of life also becomes obvious and necessary. So our description or depiction of the battery value chain here is based on the highest level of representation in 7 major industrial segments that follow the entire product life cycle over time. Mining and exploration refers to identifying, extracting raw battery materials. Processing refers to purifying them to near 100% purity as battery-grade reagents. Components refer to the anatomy of a battery, those anode, cathode, electrolyte, and ancillary components that are assembled from the battery-grade reagents that are inside the cell, which is the first semi-finished product in the value chain. And those cells are assembled in series and parallel with outside the cell components into packs. Packs are integrated into applications, which then interface with consumers. And along the way, at every step, there are reuse and recycling and circularity options for reintroducing waste back into the supply chain. So this is a pretty powerful framework. It's been invoked already several times in today's meeting, and it captures the direction of materials and energy flows and even commercial interactions related to the production and operation of batteries. And we can also map key stakeholders by the battery value chain framework, which we will see later on. And in the case of our own organization, in OERD, we have multiple teams. I mentioned 14. And our battery team, we're focusing on the middle of the value chain, but we have a line of sight on the whole thing. And our other teams in OERD have lines of sight on other aspects of the value chain. Okay, next framework is the battery performance framework. And this shows the requirements of a battery's end-use application, which I really appreciated when I spent time in industry. And those can be mapped onto five key battery performance metrics: energy density, power density, safety, lifetime, and cost. This is true at a high level, and then we can think about several sub-metrics that could be grouped under these categories, be it low temperature performance, continuous power, peak power, etc. And this framework came up in the earlier session, just thinking that when we're talking about silicon versus lithium metal, which will win. And part of the answer was battery material, cells, and packs ultimately determine the end-use application's performance envelope, which must meet or exceed the targets defined by the application requirements, which are different for an EV or for medium and heavy duty transportation or a starter battery or stationary storage. And so this framework prompts evaluators of battery technologies to consider all of the requirements of the application together instead of focusing on one or a few. So framing battery innovation in terms of this gap, let's say, between requirements and performance, researchers and decision makers, we can more objectively assess and evaluate projects and the pathways to commercialization. The final framework is the scaling and technology readiness framework, which recognizes first that batteries have a modular design and favor mass producibility, which has played a large role in their widespread adoption and falling costs. TRL, or technology readiness level, is already a widely adopted and semi-quantitative framework that is used to evaluate technological maturity from basic research through applied R&D, demonstration, and market-ready deployment. And each level carries a certain amount of technical and financial risk. So at lower TRLs, there is a higher tolerance to the risk of failure, while innovation at high TRL is more sensitive just due to the high cost of investments to do an experiment at that scale. So this version of TRL is adapted for cells, but in theory, it could be applied to any value chain segment. And this was inspired from James Frith. And it highlights what TRL would look like for cells. So validation in larger format cells produced on industrial equipment holds the most weight in terms of appreciating the technology readiness level compared to coin cells, for example, which may be suited for low TRL innovations and academic research. So this framework also highlights the need to think about all stages of innovation just from the outset, to think about manufacturability, quality control, defects, automation as soon as possible. So those were the five frameworks and form the core of our thinking. And the next part of the presentation will be showing how we are operationalizing that. So we use those frameworks to identify some innovations of interest. And without going into too much detail, I'll just enumerate from left to right. But you can see how, just by introducing these concepts, where the battery frameworks fit in. So material substitution, abundant battery chemistries and affordable batteries, application-guided battery innovation, vertical integration, processing, and advanced manufacturing of batteries, battery data and modeling approaches, circularity, standards and regulations, and innovative battery services and business models. So more detail about this can be found in the two links I shared in the chat. Okay, before turning our attention to battery firms across Canada, I want to talk about how we operationalize the SABI frameworks in our most recent funding call from the Energy Innovation Program, the Battery Industry Acceleration Call. So this funding call is now closed. It received 90 eligible submissions, about almost 200 total. And the request was for about $252.1 million. We are now at the late stages of due diligence, and maybe if I get invited again at a later time, I can present a little bit about those projects once they are announced. But as you can see, what I've shown here are the scoping criteria, eligibility criteria for this funding call. And you can see that all of the battery frameworks are represented in some capacity. So we see R&D and demo, that is invoking the TRL framework, where R&D, we specified TRLs 4 and 5 for R&D and demo 6 and 8, but also had minimum cell and materials criteria, 25 milliamp hours for R&D and at minimum 2 amp hours for demonstration projects. We also, in one of the priorities, the scale up of non-commercial chemistries, that's invoking the TRL and trying to move up in terms of manufacturing and focusing on that. So other call priorities, you can see the value chain represented across the right, materials, components, cell, and pack. And then if we go row by row through the priorities, we are providing funding to improve performance, which is defined through the battery performance framework, and with the components defined by the anatomy of a battery framework. So here is an example of us using those principles or those frameworks presented on the slides previous to actual programming. And the result was, or the result is, this is, although it's specific in many senses, as we've defined the call in different criteria, it's also accessible to many different technologies, form factors, and TRLs in a coherent way. Okay, so now is the second half of the presentation where I'm going to discuss or just talk about or speak to a snapshot of battery firms across Canada. Before going into some of the analysis, I'll talk a little bit about the data. Our sources included our own stakeholder engagement, as well as consolidating publicly available lists of battery firms from trade organizations like the Battery Metals Association of Canada, Accelerate ZEV, which is a Canadian trade association, and NatBat. All of the data presented here was collated from public sources. That's why we can share it. And the data set includes both foreign and domestic companies with operations in Canada, but we are tagging or doing analysis on the Canadian operations as opposed to global operations. So this figure shows 213 battery firms across Canada downstream of mining and exploration, with and we see good representation across the value chain in these pie charts. I should mention that we have excluded mining and exploration. One reason is this falls under a different federal department, but from the Battery Metals Association of Canada, a report from them, there are 800 mining and exploration companies in Canada, and 40% of them focus on metals that could go into batteries. That doesn't mean that they are necessarily going into batteries, but just gives an indication of their presence, and that is across Canada. So downstream of mineral exploration and mining, there are 213 firms, and there is presence in 9 out of the 10 provinces and 3 territories. Ontario has the most companies, followed by Quebec and BC, and in these provinces, the mobility and stationary applications are the largest value chain segment. In Alberta and Saskatchewan, processing has a higher representation. And despite being small, Nova Scotia, in the bottom right, has representation across multiple value chain segments. Now, we did some analysis segmenting the Canadian battery firms by the value chain segment. So every firm was tagged with a primary value chain segment. So 213 firms in Canada, 213 primary value chain segments. But some of these companies had presence or operation in multiple value chain segments. And that's indicated on the right here. So 56 had presence in 2 value chain segments, and 14 had presence in 3. A little bit about that. The companies so this is an indication of, let's say, vertical integration, and we found 2 kind of archetypes that fit that description. One are large companies that have the financial means to support the large capex to have a significant presence in multiple value chain segments, but the other were smaller companies working on non-lithium ion chemistries where because the value chain is not established. By necessity, having presence in making cells and packs and systems is required. Taking a look on the left side, the primary value chain segments, we can see mobility and stationary applications is the largest. And I mentioned there's quite a big presence of mining and exploration companies in Canada. But in the middle, there's 18, 17, and 18% for cell manufacturing, battery pack assembly, and notably a key bottleneck in processing, which is low at 11%. We're calling this a missing middle. Battery reuse and recycling, that is small, but that is to be expected as this is a nascent market. Next, we tag these battery firms by size and stage of development, which is an indicator of the TRL. And here there is a clear takeaway, which is by a significant margin, most battery firms in Canada are small. More than 64% or 63% are small, followed by medium, large, and then micro. Those large companies include foreign multinationals, including automotive OEMs and large value chain investments, as well as large utility scale stationary storage companies. And if we look at stages of development, which are a proxy for TRL, the tagging is representative of the say up and coming status of the Canadian value chain, where most of the companies are not yet commercial. Of the companies that are commercial, most are in the mobility and stationary segment, and these include distributors of products of imported cells and small mobility and stationary applications that are operating at a small scale. Of the large firms that have made or announced large EV value chain investments, they are mostly in the planning stage. Okay, now we instead of looking at the value chain, we're now looking at tagging by anatomy of a battery framework, in this case, the components. And so we see that all of the components that go into a battery have representation in Canada. And this tagging is inclusive of the primary, secondary, and tertiary value chain tags. So there are about 40 companies total doing components, but multiple companies can have tags in multiple for multiple components. That's why there are 77. Overall, and maybe to be expected, anode and cathode have the most tags, followed by components for non-lithium-ion chemistries and electrolytes. For anode and cathode, these are inclusive of large companies that made EV supply chain investment announcements, but also R&D companies. Then we did another level of depth. We're calling these level 2 tagging within each of those components. And as you can see, the largest contributor in anode is silicon, although there is some lithium metal presence in Canada as well. As far as cathode is concerned, we don't see any of the next generation cathode materials, but what we see are innovative ways to process and manufacture the traditional cathode materials, NMC and LFP. There's also a reasonable amount of non-lithium ion battery chemistry components. Next is the deep dive into cells. And the level 1 tags here are represented at the bottom here, lithium-ion cell being the largest, but there's also a significant presence of non-lithium-ion cells, which exceeds, let's say, the market size or market distribution between lithium-ion and non-lithium-ion cells. And then there are also cell-related services or adjacent industries, testing and modeling, advanced manufacturing, and electrode processing. So overall, we see multiple cell types and cell chemistries. They're all represented, but there is an interesting skew here, and notably a large fraction of open architecture non-lithium ion cells. So those are redox flow batteries and metal air batteries. So zooming in even further in one of the cell segments, which is the companies in Canada that actually manufacture cells, there are 15. What's excluded are cells are open architecture cells. So the flow batteries and some metal air batteries are excluded. So there are 11 lithium-ion companies making cells and 4 non-lithium-ion. And then we segmented into small and large format, which is we set as 20 amp hour cells. And of the large format cells, the ones that are planned, those refer to the large EV investments that have been announced or planned in Canada. But a lot of the cells that are produced in Canada, both small and large format, are for R&D purposes. There are actually only 2 companies we could identify that are selling cells at a commercial level, and one or maybe 2 are making large format cells. So this represents a notable gap. So to conclude, I presented our strategic approach to battery innovation, which outlines the structure of OERD's funding and non-funding supports of the Canadian battery innovation ecosystem. And I spent some, or maybe most of the time, talking about those 5 battery innovation frameworks as a basis for establishing coordination and communication across battery stakeholders from different disciplines and experience in batteries, highlighting some ways that we have actually tried to operationalize the frameworks. And I encourage you to use the frameworks as well to communicate the value of your battery work. And then we took a turn looking at the Canadian battery ecosystem, where we saw that there is good representation geographically across the value chain, representation of current and next generation battery technologies and different stages of development. At the same time, there are notable gaps, however, notably in processing to make battery grade reagents, in cell manufacturing, especially reaching commercial status, and in general, firms that have reached commercial status. As to leave on a high note, what we see is the Canadian battery ecosystem has very high technology potential, and it is primed for building a supply chain. So with that, I will end and have my contact information on the screen, and the battery innovation team looks at that email inbox. So with that, let me stop sharing my screen. And maybe we have a few minutes here for questions, or as much time as you have.